Hello everyone, this is Pascal from the University of Ziegen. This video will demonstrate the hierarchical adaptive time-triggered multi-core architecture referred to as hatma. Hatma was developed in the FRACTAL work package 4 to deliver fractal features at the hardware level, such as safety, reliability, adaptability, low power, and fractality. This video will also demonstrate the hierarchical metascheduler developed in work package 4 to generate system schedules used by hatma to adapt the system to a runtime context event. We'll briefly introduce time trigger systems and how their essential properties are used to realize some fractal features. hatma is a time trigger system developed at the University of Ziegen, and it extends the properties of time trigger systems to deliver other fractal features. We conclude the demonstration of the hatma component by showing the hatma implementation in hardware, where we test and evaluate the architecture. Next, we introduce the concept of metascheduling and how this aids adaptation in time trigger systems. We present how these systems are modeled and how runtime scenarios are adapted to. The demonstration of the hierarchical metascheduler component will conclude this video presentation. Finally, the multi-schedule graph generated by the hierarchical metascheduler is used to facilitate adaptation in hatma at runtime. We first demonstrate the hatma component. To have a system time-triggered result in tasks and activities in the system executed at defined points in time. To achieve this property, at development time, task execution times and injection times of messages are scheduled, and also the routing of these messages are also scheduled. This temporal predictability inherently facilitates fault containment, achieving real-time constraints of the application and resource control without dynamic arbitration. Furthermore, leveraging these properties allows for modularity in the design of these systems. Architectural system components are developed independently and integrated thanks to the synchronization offered by having the systems time-triggered. Prior knowledge of the system behavior at any point in time is used to identify runtime changes in the system operation. A previous understanding of this system behavior also gives a sense of system dependability. Combined with fault containment properties, time trigger systems establish safety arguments for the system and further the system's reliability. The FRACTAL platform is conceived to deliver services at the hardware level, such as system awareness of runtime operational context and the system's adaptability based on active context. The FRACTAL platform should also operate under low power constraints and offer these system services at hierarchical levels, fulfilling the fractality feature of the platform. Implementing the FRACTAL platform as a time trigger system inherently contributes to this safety and reliability of the platform. However, other FRACTAL platform features, such as context awareness and adaptation for low power at multiple hierarchies, are a challenge due to the predefined operation of the system described in the pre-computed system schedules, which are deployed in the system at runtime. A time-triggered architecture encompasses processing elements or PEs, all interconnected through a time-triggered network on chip or NOC. These PEs can be homogeneous in the case of a multi-core architecture. However, it can also be heterogeneous, where a PE is instantiated either as an application core, a memory, bare metal, or a gateway to facilitate communication between multiple nodes in a hierarchical system, all connected through a time-sensitive network or TSN. The University of Ziegen extends this time-triggered architecture to include an adaptation logic, a crucial component for context awareness and adaptability for low power. The adaptation logic facilitates hierarchical adaptation and comprises a time-triggered context monitor, context agreement unit, and a schedule dispatcher. An adaptation logic attached to a single application call forms the basis of hatma to deliver the features of the FRACTAL platform. In either implementation of the architecture, a time-triggered network interface through its ports facilitates communication of application messages through the NOC. The network interface also enables the exchange of context events represented in a bit string through dedicated ports. In case of a PE instantiated as a gateway, the network interface also facilitates communication between the nodes. The adaptation logic is responsible for adapting the system behavior to reported context through an aligned switching of the system schedule across all PEs. The next system schedule is computed at development time and is adapted based on the reported context event. The adaptation logic therefore achieves adaptation in the system through the runtime switching of pre-computed system schedules. In the demonstration of the hierarchical metascheduler, we will show how these schedules are computed and how they facilitate adaptation at low power. And in the implementation of the hatma component, we make use of the adaptive time-triggered network on chip, which is developed also in work package 4 under task 4.3. The context monitor can be represented as a state machine and is responsible for observing the behavior of the cause and generating local context information. An example of local context information is a slack event when a task executed on the call finishes before its worst case execution time. A local context can also be a failure event when an application call is unavailable to perform a task, or it could be a thermal event when the temperature of a call exceeds a certain thermal threshold. Local context event can also be a low battery state or a change in environmental conditions. The time-triggered context monitor machine reacts to an external trigger. When triggered, it transitions to the encode state, where the reported context event is encoded in a 32-bit string and driven at the output. In each case, the triggers are generated based on a pre-computed adaptation schedule. Such machine operation allows for periodic observation and reporting of context events in multiple instances. Whenever triggered, the machine encodes the reported context event in a bit string and generates a local context information at the output. Hatma supports adaptation through the deployment of pre-computed schedules for reported context events. However, the major challenge is preserving the properties of time-trigger systems such as temporal predictability, fault containment, and implicit synchronization. Therefore, all building blocks must consistently switch between these schedules. This requires a system-wide consistent information about the context events that determine this adaptation. In addition, the adaptation must work correctly across all adaptation units in the presence of faults to prevent the introduction of vulnerabilities. The context agreement unit in the adaptation logic establishes this unanimous context information across all PEs, which is globally consistent at each relevant hierarchy. The context agreement unit broadcasts local context reported by the context monitors through a hierarchical interactive consistency protocol to neighbors in a dedicated double ring communication topology. This communication topology between adaptation logic contributes to the dependability of the system, and combined with the distributed agreement of the adaptation logic, the adaptation logic itself doesn't represent a single point of failure in the system. The context agreement unit transitions to the pole state from the initial state when triggered. In the pole state, it collects the local context information reported by the context monitor. It then transitions to the write state where it broadcasts its local context to its next neighbor. The context agreement unit remains in a write-read check loop where it broadcasts its local context information to the neighbor. It reads the local context broadcasted from its neighbor and then checks this received local context against its broadcasted local context for similarities. Now it remains in this loop until when the received local context is the same as the initial broadcast of its local context, after which the context agreement unit converges. When in a converged state, all context agreement units in the network possess the same or identical context information, and this information is used to switch the system schedule across all adaptation logic synchronously based on the reported local context. The context agreement unit transitions to the pole state when triggered or returns to the initial state when it is reset. The triggers for the context agreement unit are also based on a system adaptation schedule and are synchronized across all the context agreement units. The aligned and periodic triggers for the context monitors and context agreement units allow for parallel instances or periods of adaptation. For example, an instance of adaptation can be in the distribution phase, and the next instance of adaptation can begin with the reporting phase of the context monitors. In summary, the context agreement unit collects context, reported local context from the context monitor, and distributes this context to all context agreement units in the network. This ensures that all units possess an identical context information about the system state, and this agreed context information is used to switch the system schedule, thereby preserving the system properties of this time trigger system. We will demonstrate hatma instantiated in hardware using the Xilinx Vivado design suite and VT's toolchain for synthetic Slack scenarios to validate the hatma architecture for low power services. A multi-core architecture consisting of a Zinc processing system and three microblaze cores, the adaptation logic, and the adaptive time-triggered network on chip is instantiated on the Xilinx Zinc UltraScale MP-SoC, the ZCU102 FPGA board. Hello everyone, this is Pascal Monka from the University of Zidane. In this video, I'll be demonstrating adaptation in a time-triggered single-node multi-core architecture implemented on the Xilinx ZCU102 evaluation FPGA. First, we want to make sure the FPGA is connected to power, as well as our local computer. Here we make use of two USB cables, one to allow us to program the FPGA, and the other to receive communication from the FPGA at runtime. We also make use of Xilinx Vivado and VT's toolchain to achieve this demonstration. Xilinx Vivado allows us to design and implement a single-node architecture capable of runtime adaptation. VT's, on the other hand, is a software used to create and run a bare metal application on the node. Vivado also allows us to observe the system adaptation at runtime through its integrated hardware manager. To demonstrate hatma adaptation, we created a project in Vivado targeted at the Zinc UltraScale ZCU102 evaluation board. In this project, a 4-core single-node time-triggered architecture is shown in this design. This design comprises of 3 microblaze soft cores and 1 Zinc UltraScale processing system. Communication between the cores is facilitated through the adaptive time-triggered network on chip, or ATT-NOC for short, developed in task 4.3. For each core in the design, an adaptation logic is connected to monitor the core and adapt the ATT-NOC schedule based on the observed context event. The adaptation logic comprises of a context monitor and a context agreement unit to facilitate the broadcast of context events reported by the context monitors. To allow for communication between the cores and the adaptation logic, an AXI slave is implemented through which the context monitor observes the core for Slack events. Communication between the cores, adaptation logic, and ATT-NOC is facilitated through an AXI Smart Connect. In this design, a time-triggered scheduler is implemented to schedule the system's adaptation, where a global time base provides a common notion of time used to synchronize the system components. To observe the runtime adaptation of this design to context events, an integrated logic analyzer is implemented to monitor key signals of the adaptation logic and ATT knock. We first show a behavioral simulation of this design, after which we implement the design on the Xilinx ZCU 102 FPGA. For the simulation, a test bench is created. In this test bench, a Slack event is simulated every 3 microseconds in the form of a 32-bit string. We show the results of the simulation where the system clock runs at 100 MHz. We advance the simulation for 15 microseconds to observe the behavior of the adaptation logics over this period. The TT scheduler provides a trigger for monitoring an agreement of the adaptation logics every 3 microseconds. The context monitors are triggered synchronously, where they all report any observed Slack event. In the first instance, Context Monitor 1 reports a Slack event and no event is observed by the other monitors. In the next instance, Context Monitor 2 reports a Slack event and no event is reported by the other monitors. Similarly, in instance 3, Context Monitor 3 reports a Slack event and no other event is observed by the other monitors. And also in instance 4, Context Monitor 4 reports a Slack event while no event is observed by the other monitors. Similar to the context monitors, the context agreement units are also triggered synchronously. Where they go through the poll states, where events reported by the monitors are collected and stored in local registers. In the write state, reported local events are relayed to the next agreement unit through the Hierarchical Interactive Consistency Protocol, or HICP for short. In the read state, the broadcasts are read and stored in the corresponding local registers. Each agreement unit repeats this process, in each case, checking each read broadcast against its local event. The HICP converges when the reported event is relayed back to the context agreement unit of origin. The result of this process is the agreement of all context agreement units on the Slack events reported by the context monitors in each instance. As we can see, in instance 1, all context agreement units agree on the Slack event reported by context monitor 1. Same also in instance 2, all context agreement units agree on the Slack event reported by context monitor 2. Similarly, we observe the same behavior of the context agreement units in instance 3 and instance 4, where they all agree on the context events reported by the context monitor 3 and context monitor 4 in the respective instances. For this four-core design, the time to convergence of a HICP, which is the period between the trigger for agreement and the convergence of the context agreement unit, is observed to be 200 nanoseconds. Where the earliest time at which a system adaptation is possible is observed to be 230 nanoseconds. At this point, all context agreement units agree on the observed Slack event, which is required for an aligned system schedule change. To implement this design on the ZCU 102 FPGA, we first synthesize the design. After the synthesis is completed, we run an implementation. Finally, the bitstream is generated and the hardware is exported. After the hardware has been exported, the ZCU 102 FPGA is then programmed through the Xilinx Vivado VTIS toolchain. We create a project workspace in VTIS. First, we create a platform project using the hardware exported earlier from Vivado. Here we want to select the hardware previously exported in the form of an XSA file. For the processor, we select one of the ARM cores on the Zinc PS. To demonstrate adaptation in hardware, we create a bare metal application to print a text app. To demonstrate adaptation in hardware, we create a bare metal application to print a test app. To demonstrate adaptation in hardware, we create a bare metal application to print a test hello world text to the terminal. In creating the application project, we select the hardware platform previously created as the base platform for the FPGA. Next, we input an application project name. During the execution of this application on the FPGA, hardware tasks are completed earlier than scheduled. As a result, 4 Slack events are generated at runtime. This Slack event is the difference between the actual completion time of a task and the pre-scheduled completion time of that task. We open a local terminal to display the results of the application. Here, we set up Picocom to monitor the serial pulse of the FPGA at 115200 baud rate. Next, we ensure that the FPGA is turned on and both serial and programming cables are connected. To program the FPGA, we first build the application project. This bare metal application is built with a platform project made from the exported design as shown earlier. After the build operation is completed, we then run the application on the FPGA and observe the terminal for the results of the application. As we see on the terminal, the application is executed successfully and the results are displayed on the terminal. During the operation or during the execution of the application, we observe the behavior of the hardware at runtime. During the execution of the application, we observe the behavior of the hardware at runtime through Vivado. In Vivado, we open a hardware manager where we open up a port to observe the hardware. The hardware manager in Vivado allows us to view key signals of the hardware during operation through the help of the integrated logic analyzers implemented earlier in the hardware design. Here, we rerun the application. As we can see, we observe the operation of the hardware at runtime, where the time-triggered scheduler periodically generates triggers for context monitoring and adaptation of the system. In each case, the adaptation logics agree on context events in each instance of adaptation. And at the end of this agreement, the adaptation logic generates a trigger signal to switch the system schedule. In each case, the observed context event is used to trigger a schedule change in the system. Similarly, the other adaptation logics report the same context event in each instance of agreement. And in each case, all adaptation logics synchronously send this trigger for system schedule change.